Welcome to my presentation. My name is Isaya Kisekka, an associate professor of agrohydrology and water management at UC Davis. I would like to talk to you about evaluating the effect of soil heterogeneity on root zone soil water dynamics in almond orchards using electrical resistivity tomography. This technique involves injecting current into the soil and measuring the resistance. It's based on the concept that the resistance to electrical flow in the soil is going to be affected by the degree of saturation as well as the chemistry of the pore water. And we measured several times over a number of hours during the day in order to generate the time lapse that would give us information of how root zone soil water dynamics were changing. And that's where the time-lapse mode comes in. This is a commercial farm about an hour and a half drive from Davis. And it grows almonds and walnuts, but it's characterized by soil heterogeneity. To manage this heterogeneity, the farmer divided the farm into different blocks of similar soil characteristics. For example, the blue is the heavy soil, the green is the layered soil, and the red is the light soil. The idea is that by dividing the farm into these smaller blocks of similar soil characteristics, it will help him manage his irrigation better. And we call this zone irrigation management. To understand how the soil water was changing in the root zone of different soil types and how the trees were responding, we went and measured electrical resistivity tomography measurements, as well as tree water status measurements. But in the interest of time, I'll not show all those measurements in this presentation. I will also focus on only two sites. I'll focus on the heavy soil and the light soil to simply demonstrate how this ERT technique can be used to understand root zone soil water dynamics. The red circle, or the red rectangle here is the light soil, and the two blue sites here are the heavy soil. If we start by looking at the heavy soil, okay, we measured resistance at different times. Time zero was our baseline, or the resistivity before irrigation was turned on. And then we, after periodic measurements, several minutes, we repeated this procedure. And what you're going to see is different colors ranging from blue, meaning resistivity was decreasing, to purple, where resistivity was increasing. So if resistance is increasing, the soil is drying. If resistance is decreasing, the soil is wetting. And if we look at the site C7, which was a heavy soil, you can see that as the dog goes by, the purple starts to increase. Remember, the purple is increasing resistance, which shows us roots where the trees are pulling the water, or root water uptake. And also the blue is increasing from the drip irrigation system that is on the surface. We see preferential flow here, as I've marked. And then we also see the purple here showing us where most of the roots are and pulling the water. Notice that most of this active root water uptake is in the top 1 to 1.2 meters of the root zone. And you also notice that the root water uptake is actually occurs at a faster rate than the infiltration. Okay. If we continue stepping through time, you see that this purple area continues to increase, as well as the infiltration water also continues to move down the root zone. How would the light soil behave in the same orchard? If we look at the light soil, so we start again, we had a baseline before the irrigation was turned on, we measured the resistance. and then started repeating these measurements over the day, you notice here that there is no purple, okay? Meaning that the infiltration rate in this soil, the light soils, is much faster than the root water uptake, okay? So this demonstrates the fact that we cannot manage these soils the same way, because one is going to infiltrate faster. If you apply more water, most of it is going to be lost through deep percolation. And for the heavy soils, we saw that the infiltration rate is much smaller than the root water uptake rate. So what are some of the general conclusions? We can conclude that the electrical resistivity technique is very effective in measuring subsurface soil water changes in the root zone. And secondly, most of the active root water uptake was mostly limited to the upper 0.5 meters to 1 meter of the root zone. And then finally, monitoring soil water dynamics is useful to prevent water deficits and water and nutrient losses through deep percolation. Again, thank you for watching my presentation.